Okay, when a graph does not cross the x-axis as many times as you think it should, sometimes you have imaginary roots. So we call these complex numbers. They're always in the form a plus bi. A is your real number, the number without I, and b is the imaginary number with I. Real and imaginary numbers make up the group called complex numbers. Adding and subtracting complex numbers is the same as usual. You just combine your like terms, combine your i's with i's, your real numbers with real numbers. When you multiply your complex numbers, you have to remember that when you square I, it's -1 because I is equal to the square root of -1. So when I have I squared, I'm squaring the square root of -1 and getting -1. When you divide complex numbers, you also have to remember that since I is the square root of -1, I cannot be left in the denominator. So this is the most where people will forget you have to multiply by your complex conjugate to get that out of the denominator. So I'm going to multiply these two together. It's a simple FOILing method. 3 times 5 gives me 15. 3 times 4i, 12i. Negative I times 5 minus 5i. Negative I times 4i would be negative 4i squared. 15. I'm going to combine these like terms. Positive 7i minus 4 times -1. Substitute in for I squared. That turns into a plus 4. So this is going to be 19 plus 7i. Always want my real number to come in front. Okay, multiplying the next one. Radical 3 times radical 3 is going to give me 3. Radical 3 times radical 15i. Well, 3 times 15 is 45, so this is negative radical 45i. Oh, the I is not underneath the radical, so we need to be careful of that. Okay, 15i, radical 15i times radical 3 will give me positive radical 45i. And radical 15i times negative radical 15i will give me negative 15i squared. All right, these two are going to cancel each other out. 3 minus 15 times I squared gives me 3 plus 15, which is 18. What you're going to notice is that these are called complex conjugates. They have the same real part, opposite imaginary parts. When I multiply those two together, I come out with just a real number. Okay, a couple of examples of some complex conjugates. 1 plus I and 1 minus I. 3 plus 5i. That should be a 3 minus 5i. Alright, so when I'm dividing, the only thing to simplify here is to multiply by your complex conjugate. So I'm going to rewrite the problem so everything lines up. Complex conjugate of my denominator, 4 plus 2i. Top and bottom. And I'm going to multiply across. Same FOILing method. This is going to give me 8 plus 4i plus 12i plus 6i squared over 16 plus 8i minus 8i minus 4i squared. Simplifying, I'm going to get 8 plus 16i minus 6 over 16 minus, or that'd be a plus 4. So simplify one more step. I've got 2 plus 16i over 20, and I lied, there's one more step. Everything's divisible by 2. 1 plus 8i over 10. Okay, when I have to set something equal to 0 and solve it, gotta subtract 8, so x squared equals -8. X equals the positive negative square root of -8. This is where you bring an I out. X equals plus or minus I radical 8 Hopefully you know that radical 8 is 2 radical 2. So x equals plus or minus 2I radical 2. We're going to solve one more. This one we're going to have to use our quadratic formula. So x equals negative b. This is a, b, and c. So 4 plus or minus the square root. B squared would be 16 minus 4 times a times c, so times 5 times 1, all over 2a, so 2 times 5. So x equals 4 plus or minus the square root. That's 16 minus 20, negative 4, over 10. So this is 4 plus or minus 2i over 10. Everything's divisible by 2, so 2 plus or minus I over 5.